Bismillahirrahmanirrahim. My dear student, I am Dr. Muhammad Yassin. Today we are going to discuss very important topic of fundamental of organic chemistry, that is Tautomerism. It belongs to the course Cam 1113, that is the fundamental of organic chemistry. Today we will learn what is Tautomerism, what are the different types of the Tautomerism. Of course, we will discuss in detail the Keto-enol Tautomerism, that is the type of it. Tautomerism, we will discuss in detail the mechanisms, the different proposed mechanisms of Keto-enol Tautomerism, and of course, we will discuss why Keto Tautomer is of higher stability than the enol Tautomer. We will also discuss some exceptional cases. So once again, here is a list of the key concepts that we are going to learn today. As I have already informed you that first of all, we will learn what is Tautomerism. We will go over the definition of the Tautomerism. Then we will also discuss the different types of Tautomerism with some examples. In our syllabus, Keto-enol Tautomerism is in detail, so we will discuss in detail the Keto-enol Tautomerism. Of course, we will discuss the stability of the different tautomeric forms of the Keto-enol Tautomerism. Of course, there are two tautomeric forms, keto and enol tautomer, and so we will discuss the relative stability of the keto and the enol tautomers. We will also discuss the mechanisms of the Keto-enol Tautomerism, and in the last we will see some exceptions to the stability of the Keto-enol Tautomerism. Mostly, keto tautomer has the higher stability than the enol tautomer. However, there are some exceptions in which the enol tautomer have higher stability than the keto, and we will discuss these examples in detail. So this is the overall summary or the key concept that we are going to learn in this lecture. So first of all, we will discuss what is Tautomerism and what are the tautomers. Tautomerisms can be defined as the phenomena through which a given compound can exist into two spontaneously interconvertible structures which differ only in the relative position of hydrogen. So the tautomers are the structural isomers of a compound which differ only in the position of the protons and electrons. This phenomena of the formation of the tautomer is called Tautomerism. During the formation of the tautomers or during the Tautomerism, the carbon skeleton of the compounds remain unchanged. The two different structures produced thus are known as tautomers of each other. This means the phenomena of Tautomerism takes place due to the mobility of the hydrogen atom. In a given molecule, when one of the hydrogen atom is mobile, it migrates from one atom of the molecule to another atom in the same molecule, giving two different compounds. Two isomer compounds obtained thus have similar molecular formula, but different position of one hydrogen atom are called tautomer, and this phenomena is called Tautomerism. The Tautomerism term is also known as the desmotropism. In Greek language, desmos means bond and tropos means term. As the name suggests, the phenomena involve the change of the bonds within the molecule. It is a kind of functional isomerism and involves difference of linkage of hydrogen atoms. In order to understand the phenomena of Tautomerism and the tautomers, let us consider the two structural formulas of a amino acid or reaction which involves a simple proton transfer in an intermolecular fashion is called tautomerization. So here on this slide, you may see that in the molecule number 1, the carboxylic group contains one hydrogen atom that is directly attached with the oxygen atom. Whereas in the other molecule or the structural formula of the amino acid that is labeled as 2, you may see that the proton has been shifted from the carboxylic group to the amino group, and the amino group is converted from NH2 into NH3, and it contains a positive charge, and similarly the carboxylate group is now resonance stabilized, and this structural formula that is represented with the number 2 as the deuterion form of the amino acid. So the structural formula number 1 of the amino acid and the number 2, that is the deuterionic form, are the two tautomers of each other. So, and this phenomena is called the tautomerism, and this process is called tautomerization. So the neutral and the deuterionic form of the amino acids are the two tautomers of each other, and this process during which the proton from the carboxylic group has been shifted into the amino group is called tautomerization, and this phenomena is called tautomerism. Bismillahirrahmanirrahim. My dear student, I am Dr. Muhammad Yasin. We see that Tautomerism is a phenomenon where a single chemical compound tend to exist in two or more interconvertible structures that are different in the terms of relative position of one atomic nucleus, which is generally the hydrogen. The two structures are called the tautomers and exist in dynamic equilibrium. Tautomerism is also called as desmotropism. Depending upon the distance between the two atoms involving the migration of atom, that is mostly the hydrogen atom, the phenomena of tautomerism can be classified into two major categories. Number one, the dyad system and the triad system. Tautomerism taking place in dyad system means the system that comprises of two atoms only, and the triad system, that is the tautomerism taking place in a system that comprises of three atoms only. So you may see the tautomerism, the phenomena of tautomerism in two systems, a dyad system or triad system. Now let's discuss different classifications of tautomerism. First of all, we will discuss the tautomerism in dyad system. In dyad system showing tautomerism, the migration of the mobile hydrogen takes place between the two adjacent atoms. This means it is a system of two atoms involving such tautomerism. However, due to actual migration of protons, such tautomerism is also known as 1,2 proton shift. For example, hydrogen cyanide tautomerized into hydrogen isocyanide. The chemical equation as shown on the coming slide. Here you may see the process of tautomerization of hydrogen cyanide. In the molecule of hydrogen cyanide, the hydrogen atom first gets detached itself from the carbon atom, and hence carbon is getting the negative charge, and the proton is then migrated towards the nitrogen and get attached with the nitrogen. The nitrogen is having one lone pair of electrons. It donates it to the hydrogen atom and resultantly the nitrogen atom gets the positive charge. So in this way the hydrogen isocyanide ion is a molecule is formed which is resonance stabilized, and the two resonance are the contributing structures of hydrogen isocyanide are also shown on this slide. Another example is the tautomerization of nitro group into the nitrate group. So on this slide you may see that the nitrous acid, in the nitrous acid nitro group is present, and I have also shown the dyad system. So you may see that the hydrogen is migrating and is now attaching to another oxygen atom, and hence in nitrous acid the nitro group is converted into nitrite form. The second class of the tautomerism is a triad system. In triad system showing tautomerism, the migration of the mobile hydrogen takes place between the first and the third atoms in the molecule. So here I have shown the three atoms. One is shown with the red color, the middle is shown with the pink color, and the extreme right is shown with the blue color. To one atom that is shown with the red color, one hydrogen is attached. So this is a triad system if you are ignoring the hydrogen atom. So this means it is a system of three atoms involving such tautomerism. It is also known as 1,3 proton shift. So in this system, first of all, the hydrogen atom will detach itself from the atom to which it was attached, and here in this case it is attached to an atom which is shown with the red color, and a double band is present between the middle and the extreme right atom that are shown with pink and blue color respectively. So first step will be the detachment of the hydrogen atom from an atom that is shown with the red color. In the second step, this hydrogen atom will attach itself to the extreme right atom that is shown with the blue color, and simultaneously the bond between the middle and the extreme left atom will be broken, and the bond or double bond between the extreme right and the middle atom will be formed. On this slide, you may see a triad system that is a acetaldehyde. Here, the acetaldehyde has a hydrogen atom that is directly attached with a carbonyl carbon. It readily tautomerizes into a vinyl alcohol, that is the enol form. Here the acetaldehyde is representing a keto form, whereas the vinyl alcohol is representing the enol form. You may see that the hydrogen that is directly attached with the methyl, that is directly attached with the alpha carbon, that is the methyl group, get transferred to the carbonyl oxygen, and this carbonyl oxygen is readily converted into the hydroxyl group, and hence a vinyl alcohol is formed, whereas the bond between the carbon and the oxygen, that is the carbonyl functional group, is broken, and a carbon-carbon double bond is simultaneously formed. Depending upon the distance between the two atoms involving the migration of atom, that is mostly the hydrogen atom, the phenomena of tautomerism can be classified into two major categories. Number one, the dyad system and the triad system. Tautomerism taking place in dyad system means the system that, in order to understand the phenomena of tautomerism and the tautomers, let us consider the two structural formulas of a amino acid or reaction which involves a simple proton transfer in an intermolecular fashion is called tautomerization. So here on this slide you may see that in the molecule number 1, the carboxylic group contains one hydrogen atom that is directly attached with the oxygen atom, whereas in the other molecule or the structural formula of the amino acid that is labeled as 2, you may see that the proton has been shifted from the carboxylic group to the amino group, and the amino group is converted from NH2 into NH3, and it contains a positive charge, and similarly the carboxylate group is now resonance stabilized, and this structural formula that is represented with the number. What are the meaning of the astatic and alpha hydrogen? Now let us discuss the meaning of astatic and alpha hydrogens. Astatic hydrogens means such hydrogens which are attached adjacent to the unsaturated atoms or double or triple bond. Such hydrogens are easily detachable from their parent atom. Alpha hydrogen is a hydrogen atom joined to alpha carbon. What is alpha carbon? Alpha carbon is immediate carbon atom joined to the unsaturated system. If a molecule contains both double bond as well as the alpha hydrogen, but it does not have any astatic hydrogen, then it cannot exhibit the tautomerism. Now let us discuss this situation with reference to para-benzoquinone. Before we are going to discuss the case of the para-benzoquinone, let us discuss the examples of acetophenone, butane-2-one, and propanoldehyde. All these three molecules contain alpha hydrogen that are shown with the red color. They also have electron withdrawing group, that is the carbonyl group. Due to this, all these compounds exhibit the phenomena of tautomerism. So they show keto-enol tautomerism. Here are two other examples. One example that involves the benzaldehyde, and the second example that involves the benzophenone. Both benzaldehyde and benzophenone contain no alpha hydrogen. Hence, both compounds cannot exhibit tautomerism. So the presence of alpha hydrogen is necessary. Additionally, this alpha hydrogen must be astatic. Here is the case of para-benzoquinone. Para-benzoquinone do not exhibit tautomerism. Para-benzoquinone have both alpha hydrogen as well as the double bond, yet unable to exhibit the tautomerism because it don't have astatic hydrogen. Para-benzoquinone, here you may see that the para-benzoquinone have 4 alpha hydrogen, but none of them is astatic. So that's why para-benzoquinone don't exhibit tautomerism. Now let us discuss different types of tautomerism depending upon type of the functional group involved in tautomerism. The phenomena of the tautomerism can be divided into different types. For example, first is the example of the keto-enol tautomerism, in which carbonyl group is converted into an enol group, and we will discuss this tautomerism in detail in this lecture. The second is the example of the nitro-SE and nitro-tautomerism. For example, here you may see on this slide that a nitro group is converted into an SE form, and similarly imine and enamine tautomerism involve the conversion of nitroso functional group into oxymino group, and I have quoted the example of nitroso conversion into the oxymino group here on this slide too. Similarly, amido-imidol tautomerism involves the conversion of amido functional group into imidol functional group. In thiamido-imethyl tautomerism, thiamido functional group is converted into imethyl functional group. We will, as I have informed you, that we will go into the detail of the keto-enol tautomerism, as keto-enol tautomerism is the most common type of the tautomerism and is well-known studied tautomerism. In this tautomerism, one tautomer contains the ketone group while another contains the enol functional group. If we talk about the enol, the literal meaning of enol is that a group which contains both double bond as well as the hydroxyl functional group. E stands for double bond, stands for the double bond, and O stands for the hydroxyl or the alcoholic functional group in the same molecule. So enol is a molecule that contains a double bond as well as a hydroxyl functional group. It is due to the tautomerism that the hydration of ethine cannot yield expected vinyl alcohol, but it yields the unexpected acetaldehyde. So here you may see that if you add the water molecule into acetylene or ethine, we expect that we are getting vinyl alcohol, but however vinyl alcohol that is formed is readily converted into acetaldehyde, which is the more stable form. So because of the keto-enol tautomerism, when you add the water molecule into the molecule of acetylene, first the vinyl alcohol is formed, which is readily converted into acetaldehyde, which is the more stable form of the keto-enol tautomerism. Vinyl alcohol is readily converted into the ethanol through tautomerism because it is more stable than the vinyl alcohol. Keto-enol tautomerism refers to a chemical equilibrium. So it is a point that must be noted that keto-enol tautomerism refers to a chemical equilibrium between a keto form, a ketone or an aldehyde. Keto stands for ketone as well as for aldehyde, and an enol, that is an alcohol. So the keto-enol tautomerism refers to a chemical equilibrium that is established between a keto and an enol form. Here in this tautomerism, keto stands for ketone as well as for the aldehyde, whereas the enol stands for alcohol that has a double bond as well. The keto and enol forms are said to be the tautomers of each other. Interconversion of the two forms, that is the keto and the enol form, involves the movement of an alpha hydrogen atom and the reorganization of the bonding electrons. So in keto-enol tautomerism, a carbonyl containing compound is normally in rapid equilibrium with an enol tautomer, which contain a pair of double bonded carbon atoms adjacent to the hydroxyl group. So here in this equation you may see that the alpha hydrogen that is present in a carbonyl containing compound, that is ketone, here is rapidly shifted towards the carbonyl oxygen, converting the ketone into an enol. And similarly in the enol, the hydroxyl group that has the hydrogen atom of the hydroxyl functional group is rapidly shifted towards the alpha carbon. The keto form predominates at equilibrium for most of the ketones. So in the keto-enol tautomerism, in the majority of the cases, the ketone form or the keto form predominates, have the higher concentration under the normal conditions. However, there are some exceptions that we will also discuss in this lecture. In these exception cases, the enol form predominates. As I have already informed you that in keto-enol tautomerism, a carbonyl containing compound is rapidly converted into an enol, and enol is rapidly converted into a keto form, and these two species exist in a dynamic equilibrium. So this phenomena is called keto-enol tautomerism. Now if we talk about the mechanism of conversion of keto form into an enol and enol into keto form, these mechanisms are always acid or base catalyzed. Acid catalyzed conversion of an enol to the keto form proceed by a two-step mechanism in an aqueous acidic solution. It is necessary that the alpha carbon atom contains at least one hydrogen atom known as the alpha hydrogen. So this is the condition for the keto-enol tautomerism, that at least one hydrogen atom of the alpha carbon must be acidic. The alpha hydrogen atom must be additionally be positioned such that its main line are parallel with the antibonding pi orbital of the carbonyl group. So these are the conditions for a keto-enol tautomerism. What are the meaning of the acidic and alpha hydrogen? Now let us discuss the meaning of acidic and alpha hydrogens. Acidic hydrogens means such hydrogens which are attached adjacent to the unsaturated atoms or double or triple bond. Such hydrogens are easily detachable from their parent atom. Alpha hydrogen is a hydrogen atom joined to alpha carbon. What is alpha carbon? Alpha carbon is immediate carbon atom. The shifting of the alpha hydrogen to the carbonyl oxygen is a concerted step. What is a concerted step? Concerted step is a chemical reaction or the step in which the bonds of the reactants are broken and the bonds of the product are formed simultaneously. So this is a concerted step with the oxygen atom in the hydroxyl group donating the electrons to produce the eventual carbonyl group. The general reaction for the acid or base catalyzed keto-enol tautomerism can be written as shown on this slide. Here you may see that the alpha hydrogen of the acetone I have shown in the red color. All the 6 hydrogens are the alpha hydrogen in the case of acetone. I have only shown the 1 hydrogen in the red color that I am going to shift towards the carbonyl oxygen. So it is the acid or base catalyzed process. So in the intermediates are the resonance stabilized intermediate products that I will show in the coming slides. What are these the resonance stabilized intermediates? These resonance stabilized intermediates are further converted into the enol form by the acid or the base. So in the enol you may see that the alpha hydrogen has been shifted towards the carbonyl oxygen and the carbonyl double bond has been broken. Instead, a double bond between the carbon-carbon is formed. So it is the enol form. So these keto and the enol forms are rapidly interconvertible, and under the normal conditions in majority of the keto-enol tautomerisms, keto forms predominate. On this slide, you may see a triad system that is a acetaldehyde. Here, the acetaldehyde has a hydrogen atom that is directly attached with a carbonyl carbon. It readily tautomerizes into a vinyl alcohol, that is the enol form. Here, the acetaldehyde is representing a keto form, whereas the vinyl alcohol is representing the enol form. You may see that the hydrogen that is directly attached with the methyl, that is directly attached with the alpha carbon, that is the methyl group, get transferred to the carbonyl oxygen, and this carbonyl oxygen is readily converted into the hydroxyl group, and hence a vinyl alcohol is formed. whereas the bond between the carbon and the oxygen, that is the carbonyl functional group, is broken and a carbon-carbon double bond is simultaneously formed. Here on this slide, I have shown the reaction mechanism for base catalyzed keto-enol tautomerism. In this step, in the conversion of the keto into the enol, the first step is the abstraction of the alpha hydrogen. So the abstraction of the alpha hydrogen by a base generates a carboanion, which is resonance stabilized. The resonance stabilized intermediate first abstract the proton from the water molecule, thus generating an enol. Similarly, during the conversion of enol into a keto tautomer, the first step is the abstraction of the proton from the hydroxyl functional group from the enol molecule. So it again generates a resonance stabilized carboanion, which is stabilized by adding a water molecule, by adding a proton from the water molecule and thus generating a keto tautomer again. So both the conversion of a keto into the enol and the conversion of the enol into the keto tautomers are shown on this slide. And we talk about the stability of keto tautomer. In case of simple aldehyde and ketone, the proportion of the keto form predominates over that of the enol form. For example, equilibrium between acetaldehyde and vinyl alcohol, proportion of the acetaldehyde is about 99.5%, while that of the vinyl alcohol is 0.5%. In the case of equilibrium between the acetone and prop 1-in-2-ol, the proportion of acetone is about 99.7%, while that of prop 1-in-2-ol is only about 0.3%. So in the majority of the cases, if we talk about the simple aldehyde and the ketone, the proportion of keto tautomer predominates over the enol tautomer. What are the meaning of the acidic and alpha hydrogen? Now let us discuss the meaning of acidic and alpha hydrogens. Acidic hydrogens means such hydrogens which are attached adjacent to the unsaturated atoms or double or triple bond. Such hydrogens are easily detachable from their parent atom. Alpha hydrogen is a hydrogen atom joined to alpha carbon. Two theories to understand the greater stability of keto tautomers are the bond enthalpy value. Number one, the bond enthalpy value. It is a well-known fact that higher value of the bond enthalpy gives higher stability to the molecule. In case of ketonic tautomers, the bond enthalpy value of the carbon-oxygen double bond, that is the carbonyl functional group, is about 362 kJ per mole. This value is much higher than that of the carbon-carbon double bond, which is about 252 kJ per mole. That is why that the ketonic form predominates over the enolic form. The second theory that accounts for the high stability of keto-tautomer is the presence of polar solvents like water. Polar solvents like water, methanol and acetic acid increases the stability of keto form because they form intermolecular hydrogen bonding with oxygen of ketone. Enol already have intermolecular hydrogen bonding because these are not affected. This is supported by the fact that the proportion of the keto form of acetyl acetone is about 25% in ethanol, which is a polar solvent, but there is of only about 7% in hexane, that is a non-polar solvent. So you may see that as the polarity of the solvent will have increased, the concentration of the keto form of acetyl acetone is also decreased from 25% to 7%. There are, however, some exceptions in which enol form is exceptionally stable. For example, in acetyl acetone, the enolic form is about 76%, while that of the ketonic form is only 24%. This is due to the intramolecular hydrogen bonds formed in enol. Similarly, in phenol, the proportion of enolic form means the phenol itself is higher than cyclohexa 2,4-diene-1-one, that is the ketonic form. This is due to the fact that three alternate double bonds in phenol stabilizes it due to the resonance energy. Here on this slide, you may see that the acetyl acetone, that is the enol form of acetyl acetone, is exceptionally stable because of the intramolecular hydrogen bonding. Similarly, in the case of, if we compare the structure of the phenol with that of the cyclohexa 2,4-diene-1-one, the phenol is the enol form, whereas the cyclohexa 2,4-diene-1-one is the keto form. The phenol is exceptionally stable because of the presence of three alternative bonds, that is a benzene ring, whereas in the keto form this benzene ring is lost. So the enol form of the acetyl acetone is exceptionally in high concentration because of the presence of intramolecular hydrogen bonding, which is absent in its keto form. And similarly, in the case of the phenol, if we compare the concentration of phenol with that of the cyclohexa 2,4-diene-1-one, the stability of the phenol because of the presence of the benzene ring make it in high concentration, and it is stable over cyclohexa 2,4-diene-1-one, that is the keto form. So what we have learned that tautomerism is a type of constitutional isomerism in which same molecule exists in more than one form that differ only in the position of the protons and electrons. Tautomers exist and can be separated, whereas the resonance structures don't exist and cannot be separated. Keto-enol tautomerism is a type of tautomerism in which mostly the keto form is most stable form, whereas there are some exceptions in which the enol form is more stable than the keto form. Two theories to understand the greater stability of keto tautomers are the bond enthalpy value. Number one, the bond enthalpy value. It is a well-known fact that higher value of the bond enthalpy gives higher stability to the molecule. In case of ketonic tautomers, the bond enthalpy value of the carbon-oxygen double bond, that is the carbonyl functional group, is about 360. Here is a list of the recommended books: Introduction to Organic Chemistry by John Wally and Sons. And similarly, the second book is written by M.A. Yunus, Textbook of Organic Chemistry, published by Ilmi Kitab Khana Urdu Bazaar Lahore.